So hi everyone, I welcome you all to the sixth lecture on thermal properties of matter. So today I will be going to start the lecture with Newton's law of cooling. So Newton's law of cooling, as you see that so it's related to cooling, means to say that the temperature will decrease. So if you see when we put a glass of or put um, hot any hot, let's say if it's a hot milk, then it begins to cool such that if the temperature of this milk is, let's say, Tm or some temperature T and surrounding temperature is Ts, so T should be greater than Ts. So due to that, there is a cooling is happening. But we want to study here, we want to study how fast or slow is this cooling process. Okay. So to study that, there is one experiment uh, done as shown in NCRT. So let's say take some water. So let's take some water. Let's say 300 ml. That's an activity from NCERT. So it's a calorimeter actually. So it's a calorimeter where we have a stirrer. So we have a stirrer there. So this is 300 ml water in a calorimeter with a stirrer and cover this with a two-hole lid. So let's cover this with a two-hole lid. So that's the lid. These are the holes covered with a two-hole lid. So from the one hole, there is a stirrer. So okay, instead of putting a stirrer like this, let's put it like this. So in one hole, it's a stirrer, and another, it's a thermometer. It's a thermometer. This is a stirrer. Okay, so we have to make sure that the stirrer and the thermometer is dipped in the is immersed in the water. Now note the reading of the thermometer. Now note the reading of the thermometer. However, T1 is the temperature of surrounding. Okay. So T1 is the temperature of the surrounding. So we need to heat the water in the calorimeter. So heat the water in the calorimeter till it attains a temperature of 40 degrees centigrade above room temperature. So that is T plus 40, T1 plus 40. Then stop heating the water by removing the heat source. So in the calorimeter, there is a heat source. That is, there is a heat source. So then there may be a calorimeter where there is an integrated heat source. Then stop heating the water by removing the heat source. Okay, so now till now what happened is now the system, now the temperature of this water is temperature is let's say TW, that is 40 some T1 plus 40. Okay. Now what we have to do now, take a stopwatch, take a stopwatch and start reading the thermometer after fixed interval of time. Say that after every after every 1 minute. Okay. So say that after every 1 minute of stirring, gently with the stirrer. Now we are taking the temperature, and what is happening like now, because when we remove this heat source, as soon as we remove the heat source, the temperature of this water is higher than the surrounding, and due to this there is a heat dissipation, and stirrer is sort of uh, uniformizing that thing. So we need to continue the note the temperature such that we need to we need to we need to read the temperature till it goes to T1 plus 5 degrees centigrade. T1 is the temperature of the surrounding. Okay. And then we need to plot this data. Then plot a graph by taking by taking each value of temperature delta T such that T2 minus T1. T2 is the temperature, or I can, it's TW minus T1 along y-axis with time along x-axis. And what we found out is that the plot comes like to be something like this. So that is delta T with time, and plot comes out to be okay, something like this. That is delta T in degree centigrade and time in minute. So from what is the significance of getting this plot? So the significance of getting this plot is that from the above plot we can infer that how the cooling of water is time dependent. Why we are saying that it is time dependent? Because if you see, if you plot, if you see the slope, so the slope is steeper here than here, and as you go along, the slope gets decreased. The slope is decreasing and not constant. Slope is dt by dt is decreasing, which is not a constant. So that's why from here we can directly infer that temperature is dependent upon the time. So if you see that initially the rate of cooling is high, the slope is high, but as soon as we go along, the slope decreasing and the rate of cooling is also decreasing. So the first point is initially rate of cooling is higher and decreases as the temperature of the body falls. The above activity shows that the hot body loses heat to its surroundings in the form of heat radiation. Newton's was the Newton was the first one to study this dependence of rate of cooling with time. And if we come up with the theoretical modeling of this thing, or according, we can say according to Newton's law of cooling, the rate of, according to Newton's law of cooling, the loss of heat is directly proportional to the is directly proportional to the difference of temperature difference of temperature of the body and the surrounding. Basically, we know that this curve is coming, we know that the slope is not constant. Then what does it mean? So how can we find out the slope? So to and on which factors that slope is dependent. So from here, from that, according to Newton's law of cooling, from there we will be able to get that. One assumption is that this law is valid for small temperature differences. So we can write dq by dt. We know that is directly proportional to T2. So T2, I'm saying TW minus T1. So in this case, it's temperature of water, or if for generalized TW is, let's say T2. Let's call TW is T2 for general any body. So minus dq by dt, remove proportionality and we put some constant. So this is not a thermal conductivity. Keep this in mind, into T2 minus T1. So K is the factor that depends upon area and nature of the surface of the body. Surface of the body. Suppose the body of mass M and specific heat S is at temperature T2 if the temperature falls by a small amount dP2 in time, dt, then the amount of heat loss is Q dq is equals to m as dt2, and so dq by dq by dt is m as dt2 by dt, and we know this is nothing but minus t2 minus t1 into k. So m as dt2 by dt comes out to be minus k t2 minus t1. So let's integrate this. For integrating, let's take dt2 dt2 by t2 minus t1 is equals to minus k by ms dt. Let's call it capital K. And so what we get is log ln, and because the base is e, t2 minus t1 is equals to minus kt plus c, or we can write t2 to be t1 plus c prime e to the power minus kt. C prime is, it's a constant, you can take it anyway, e to the power c. It's coming like this. So we know t2 is t1 plus c prime e to the power minus kt. So from here we can say that t2 minus t1 are actually proportional to e to the power minus kt. So that's the curve also. If you see this plot, then you will get to know that how this is coming with respect to time. So delta t is something exponential to the time. Okay, so that is Newton's law of cooling. If in the question it asks the plot between ln t2 minus t1 versus t, then don't get confused, because if you take ln, then it's a linear plot, because ln of this ln t2 minus t1 is directly proportional to minus, actually not proportional, it's c prime is c prime minus k t. Okay, so that is, this is negative slope of, so that's a negative slope. So that is all new about Newton's law of cooling. Now let's look at the another concept, that is radiation. So I will be going to introduce and try to give you a feel of radiation. So radiation is nothing but it is another process that includes heat transfer, but it doesn't require any medium. Okay, and in more formal way, I can say radiation, it is a process involving the transfer of heat from high temperature to low temperature and does not require any media. So unlike conduction, it is different from conduction and convection. Conduction and convection, because it requires, because in both of these we need some molecules, because in both of these we need media, or let's say molecules, to transfer heat. The important point is that thermal radiations thermal radiations is generated when heat from the movement of charges in the material. So those charges are electrons and protons. So you can see that when we are having a motion of electrons and protons, then it means to say that the temperature is very high. So from the movement of charges in the material is converted to electromagnetic radiation. Okay. So what are EM waves actually? So this thing is proven by, so Maxwell proved that any radiation is EM wave. These waves are EM wave is electromagnetic waves, and these waves are formed by the superposition of electric and magnetic field. So these waves are formed by the superposition of electric and magnetic field perpendicular to each other, each other. So it's like something like this. If we have this sort of, if you say there's a sinusoidal electric field E propagating in time or propagating in space, then This wave is, so this is perpendicular to that. This is perpendicular to that. So if this is electric field, then this is magnetic field, and this is a EM wave. So that is all about radiation. So let's look at the some of the properties of radiation. So sorry to say this lecture is a bit theoretical lecture. So let's quickly look at the different properties of radiation that are. So first I write the what are those properties and then we'll explain what is that. So all objects emit radiation simply because their temperature is above absolute temperature, or we can or it's above absolute zero, and all objects absorbs heat or radiation falling on it from another object. So here absolute zero means to say that, so that means we know absolute zero is 0 Kelvin or minus 273.15 degrees centigrade. So this absolute zero is the system, thermodynamic system, thermodynamic system has the lowest energy at absolute zero. So just for, so if the temperature of the body is more than the absolute zero, then there is a possibility of radiation. Another property of radiation is, so as I told you earlier, that Maxwell in his theory of EM waves proved that all radiations are EM wave and their source are vibrations of vibrations of charged particle in atom and molecule. So we have if we, let's say we take atom, so we have a nucleus, an electron in outer in some orbit, and that is rotating. And due to that, so where the when the temperature is above absolute zero, then there is a vibration of these proton and neutron, proton and electron, and due to which it emits a electromagnetic wave. And that EM wave, so that's a radiation in the form of EM wave. Another point is more radiations are emitted at a higher temperature in compared to that of lower temperature. This means to say that as you increase the temperature, the radiation or the intensity of radiation, which we called as an emissive power, I will tell you later, it increases. Yeah, or we can say the intensity of radiation increases with temperature. So another point is that's the point of Wey's displacement law, but I'm telling you here that the wavelength corresponding to maximum emission of radiation shift from longer the lambda. So lambda is wavelength here corresponding to maximum emission of radiation. Radiation shifts from shifts from longer to shorter wavelength as temperature increases, and that is Wien's displacement law. We will look at it in more detail. And due to this only, due to this, you see, you observe as the temperature of the body changes, the color also appear to be changed. So if you have a body, if you increase the temperature, then because of that change in wavelength, that shift in wavelength, the color of the body is changing. These radiations are allowed to travel through vacuum because these are EM waves. Radiations can travel to vacuum as these are just EM waves. And because these are EM waves, so similar to light, similar to light, these can also be reflected, refracted, diffracted, and polarized. So radiation from another point is that radiation from point source follow inverse square law. So if a point source like consider a sphere, then the radiation is inversely proportional to the radius square. And the last and foremost point is that thermal radiations travel with speed of light and in a straight line. So these are nothing but the property of EM waves. Okay. Okay. So this is the introduction of radiation. After that, so what we have covered in this class is the Newton's law of cooling. So we have covered the Newton's law of cooling. Then I told you that that rate of cooling is dependent on time. So initial rate of cooling is higher compared to as we move along with time. And this is the experimental plot that is that is we have shown with the help of the activity given in NCRT. Then we have new we told that how it is related by the Newton's arguments, and we got this same kind of formula. So that is nothing but the logarithmic variation. If you plot delta t with time, so that's the logarithmic variation. If you put if you plot ln of uh, t2 minus t1 with time, then it become a straight line. After that, I introduced the concept of radiation, and it's a bit theoretical. And in the next lecture is will also become a bit theoretical, where the radiation we will be continuing the radiation. But you need to know all of these properties well. Some of the properties of this radiation are just the properties of electromagnetic waves, because radiation is nothing but the electromagnetic wave. So in the next lecture, we will cover EM waves, sorry, radiations in detail, and we'll wrap up the thermal properties of matter. Thank you.